Greetings everyone, hope you are all feeling well. I'm Abbas Khalili. This presentation is on throughput of millimeter wave MIMO systems with low resolution ADCs. This is a joint work between New York University, University of Waterloo, and Weizmann Institute of Science. This work was accepted to ICAST 2020. As you might be well aware, millimeter wave and massive MIMO are two promising technologies envisioned for the next generation of wireless networks. Both these technologies rely on using large antenna arrays to perform spatial multiplexing and beamforming. However, using large antenna arrays comes at the cost of high power consumption. What's the reason of this high power consumption? Well, in the conventional receiver design, it is assumed that each antenna is connected to a RF chain which is connected to a high resolution ADC. This receiver is often referred to fully digital receiver. And as you can see, the power consumption of this receiver increases linearly with the number of antennas. Moreover, the power consumption of an ADC increases exponentially with respect to its number of output bits. So high resolution ADCs become a major source of power consumption in these receivers. So what can we do? Well, one can reduce the number of RF chains, which has led to the design of hybrid and analog receivers, or reduce the resolution of the ADCs, or both. In this talk, in order to reduce the power consumption, we are going to focus on MIMO receivers equipped with a small number of 1-bit ADCs. However, reducing the power consumption would also degrade the performance of the receivers with respect to the full digital receivers with high resolution ADCs. So in this talk, we are interested in answering three main questions. The first one is, what performance can we achieve in practical millimeter wave system? Second one is, how much loss do we have using a small number of 1-bit ADCs? And lastly, how much loss do we have due to the channel estimation? Well, as a preview of the result, we consider millimeter wave downlink scenario and show that indeed using a small number of 1-bit ADCs, you can achieve performance close to that of the full digital receiver with high resolution ADCs. And also channel estimation with this receiver does not degrade the performance, the data rate much. Before going to the results, let me explain some of the related literature on this topic. In 2017, Mo et al. Considered hybrid receivers with few-bit ADCs and developed achievability schemes using channel inversion and singular value decomposition methods. In 2017, Rini et al. Proposed a general framework to analyze MIMO receivers with 1-bit ADCs. And using this framework, they provided bounds on capacity of several receiver structures. In 2018, we used this general framework and provided bound on the capacity of MIMO system with 1-bit ADCs using geometric insights. In 2019, we, in two separate papers, developed two new receivers, namely blockwise analog receivers and adaptive terrestrial receiver, and showed that these two receivers achieved the highest rate among all receivers with the same number of 1-bit ADCs at high SNR. In this work, we are going to consider the adaptive terrestrial receiver and investigate the performance in practical millimeter wave systems. This figure shows the block diagram of adaptive terrestrial receiver. As you can see, the channel output are first fed to a linear analog combiner, whose output are given to a set of 1-bit ADCs. As you can see, the threshold of these 1-bit ADCs have two components: a static component, which is fixed throughout all the time slots, and a dynamic component, which is adaptively changed based on the output of the ADCs in the previous time slots. We analyzed this receiver and derived closed form expression for the achievable rate in point-to-point broadcast and multiple access channels. To explain how this receiver works, let us consider a simple example. In this example, the receiver has one antenna and two 1-bit ADCs. And we are going to use these symbols for transmission. At the first time slot, we are transmitting the signal -A, and the second one +A. In the first time slot, as you can see, the threshold of the first ADC is 0, and it performs sign quantization. So At the first time slot, the signal minus A is received, and W1 would be -1, which is the first bit corresponding to the symbol -A. And meanwhile, the second 1-bit ADC does not give us anything, since the input is delayed and there is no input to the second 1-bit ADC. In the second time slot, we see that the output of the first ADC is given to the second 1-bit ADC and changes its threshold. Meanwhile, the symbol -A is going to be quantized using this new threshold, and this way we are able to decode the second bit, which is +1. Meanwhile, the first ADC is going to quantize the second channel output, which is +A, and give us the sign of that, which is +1. And this process continues in the similar fashion. There are a few important observations here. One is that we were able to construct a 2-bit ADC using two 1-bit ADCs. And in general, using adaptive threshold receiver, one can construct a B-bit ADC using B1-bit ADCs. Another important observation is that there is no latency involved, meaning that aside from the first time slot, when we get 1 bit, in the rest of the time slot, we are getting 2 bits per channel use, which is the maximum, which is the limit of the system and cannot be improved. We also note that one can utilize successive approximate register ADCs, and which are proposed for low power consumption application to achieve a similar effect. Now let me explain the downlink achievability scheme that we are considering. This achievability scheme is optimal in the sense that at high SNR, all of the users will achieve the rate equal to their number of 1-bit ADCs. In this achievability scheme, the base station and the users perform SV singular value decomposition on the channel to equivalently create a set of parallel subchannels. Then the base station will allocate its transmit power and the users their 1-bit ADCs among these subchannels. For transmission, the base station uses time division multiple access with equal time shares. And to explain what what symbols it uses and modulation scheme it considers, let's consider a subchannel which is allocated B1-bit ADCs. The user will utilize this B1-bit ADCs to perform NB-bit quantization throughout n time slot of the received signal through this subchannel. And this way, the user is decoding the signal even when the base station is not transmitting to that user and is transmitting to the other users. And this is one of the key reasons that this architecture achieves the optimal high SNR rate. To achieve the optimal high SNR rate, we are considering that the base station uses 2 to power NB PAM modulation to transmit through this subchannel. Using this achievability scheme, we get this closed form rate expression for the rate of the users, where this maximization is over the transmit power and ADC allocation. This optimization is equivalent to solving a mixed integer programming problem, which is known to be NP-hard. And to avoid that, we are considering several low complexity heuristics. The first one is WPUA, which performs water filling for power allocation and uniform ADC allocation at the users. The second one is UPUA, which performs uniform power allocation and uniform ADC allocation. And the last one is SPSA, which allocates all the transmit power and ADCs to the strongest subchannel. Before showing the performance of this receiver using these heuristics, let me explain the simulation assumptions that we have. We consider downlinking millimeter wave single cell system, and we are using the cluster channel model. Due to practicality constraints, we are limiting the modulation order to 256 QAM, which is equivalent to 16 PAM per dimension. And for modulation symbols, we are using uniform input distribution. We also assume perfect channel coding, meaning that we are not incorporating the effect of block error rate in our simulations. And also for our first simulation, we are assuming perfect channel state information. The other important system parameters are listed in this table, For the user, we are using 16 antennas, and for the base station, we are allowing for 64 antennas. In this figure, we see the empirical CDF of the achievable rate in where there is only one user, and the user is equipped with 8 1-bit ADCs. As for the upper bound and performance benchmark, we are using truncated channel capacity. The reason that is truncated at 8 bits per channel use is that since the user has 8 1-bit ADCs, its rate cannot increase 8 bits per channel use. As we can see, the WPUA heuristic achieves near optimal performance in all the rate regions. And this means that using complex optimization scheme would only give us marginal gains. And so WPA-UA is a good scheme. And complex optimization is not needed. Also, we see that at the low rate region, SPSA scheme achieves the best rate complexity trade-off. These are the observations which I just mentioned. As I mentioned in the beginning of the talk, we are also interested in the impact of channel estimation. For the channel estimation, we assume that the base station transmits a pilot sequence of length 512, and during this transmission, the users allocate 3 1-bit ADCs per dimension per antenna. Then users perform channel estimation using EM-GAMP algorithm. This algorithm uses the sparsity of the channel millimeter wave channel to improve the performance of the channel estimation. After performing the channel estimation, the base station and the users configured their transmit power and ADC allocation using WPUA algorithm. In this plot, we see the empirical CDF of the achievable rate when there are 10 users. And we use only 8 1-bit ADCs for each user during data transmission. As for the upper bound, we are using channel capacity with TDMA, and the reason is that since we are using time division multiple access protocol, we cannot beat channel capacity with TDMA. And in the case of perfect CSI, we see that we are very close to the optimal. And in case of estimated CSI, we see that in the intermediate and high rate region, we are close to the optimal. However, in the low rate region, there is this gap. And the reason is that at low SNR, the channel estimation error is high. We note that even though we use 3 1-bit ADCs per dimension for channel estimation, which is equivalent to 96 1-bit ADCs, for data transmission, we only need 8 1-bit ADCs to achieve near optimal performance. These are the observations which I just mentioned. And in conclusion, we consider downlink millimeter wave system with adaptive threshold receiver, and we showed that using a small number of 1-bit ADCs and a low complexity algorithm for power and ADC allocation, we can achieve a performance, data rate close to that of the fully digital receiver with high resolution ADCs. And also we showed that the channel estimation with 1-bit ADCs does not degrade the data rate much. Thank you for your attention and have a good day.